Hello everyone, so in the last video I kind of walked us through what the definition of the limit is and kind of explained why it's sensible to define it that way. So we should be maybe a little more comfortable with this definition and what it means, but let me write it out and quickly go through it anyways. So the limit as x approaches a of f of x equaling L. This is basically defined as this. So for all epsilon greater than 0, there exists a delta greater than 0 such that our following implication holds. And this implication is the distance between x and a is greater than 0 and less than delta implies that the distance between f of x and L is less than epsilon, right? So this is saying that we can always get x values within a window small enough, so within this window, for the corresponding f of x values to be close enough to a proposed value L, to be sufficiently close, right? Essentially, we're able to get arbitrarily close to the L value, no matter what we define as close, no matter what epsilon value we use. So this definition really gets at this approaching intuition we have with limits. So we know the definition, but how can we actually use it to formally prove limits? Well, we first always write what we know. So one is write what we know. Write the givens. So we know that epsilon is greater than 0, right? We know that delta holds some value, it takes on some value, equals something, but we are not sure of what it equals for now. We actually discover what it equals when we go on with this proof. Um, so finally, after this, we kind of assume the hypothesis, this piece over here. So we assume this hypothesis that the distance between x and a is less than delta. And our job is to show that when we assume these things, that we get to our consequence, that we are able to show that the logical consequence of these assumptions is that f of x, the distance between f of x and L is truly less than epsilon.
So one thing to note is that this delta value will usually change according to what epsilon value we have. It'll usually be in terms of this epsilon, because as we shrink or as we change our epsilon window, we would want to change the delta window accordingly, so that the corresponding f of x values always remain within this always remain within the epsilon window. So here I just graphically showed the limits as x approaches a of f of x equaling L, and this blue line is just the f of x, it's just the line. And we see that we have our epsilon window in red. This just is the window around L. And we have also our delta window in purple, and the corresponding f of x values coming out from this delta window within these dotted green lines. So we see that if we set delta to a constant, like for example 1, this may work for epsilon equaling 2.8. We see that this green boundary, the corresponding f of x values are always within the epsilon tolerance. However, I believe once we set epsilon less than 2, then it won't work. And remember, for the limit to exist, it has to work for whatever epsilon we choose that's greater than 0. So using a constant delta will never work, because you can always make epsilon which is smaller than the corresponding f of x values, or for which the f of x values always come out of the epsilon window. So we would want to make this delta window in terms of epsilon. And in this case, it would be epsilon over 2. I'll show you like how you would come up with such an answer, how you'd actually come up with a specific value for what delta can equal, but here's just epsilon over 2. So we see that the green boundary and the red boundary overlap, so this is like kind of like the maximum delta can be. And we see that whenever we change the epsilon window, the delta window changes accordingly so that the f of x values always fit within this epsilon window. And the epsilon over 2, it can be anything less than that as well, like epsilon over 3. Now the f of x values are always like comfortably within this boundary. Epsilon over 4, 44, anything really smaller. So now that we know this, I will go through an example with you.
So here's an example. So let's say that we're proposing that the limit as x approaches 8 of the function 2x plus 1, that is equal to 17. So we would intuitively know this because in this case, we kind of all know that we can just plug in 8 for x and then we get 2 times 8, 16 plus 1, which is 17. But then if we want to, but we may want to formally kind of prove it, right? So in this case, we would need to use the epsilon-delta definition. So let me write it out again, except specific for this example. So for all epsilon greater than 0, there exists a delta greater than 0, such that the distance between x and instead of 8, this time 8, this is the specific value in this case, is less than delta but greater than 0, implies that the distance between the function, which is 2x plus 1, and our proposed value for the limit is bounded in this epsilon window. So here is kind of our definition for this specific limit, right? So we first want to write our givens. The givens are that epsilon is greater than 0, delta holds some value, and the distance between x and 8 is less than delta. So now one of the funny things with proofs is that we kind of start at where we want to get to. So we start by saying that our function, which is 2x plus 1 at the distance to 17, we kind of like start with this piece, and then our goal is to algebraically manipulate it in order to get it in terms of some of our given piece of information, so that we can kind of use some of our given pieces of information. So I'll show you what I mean. So this is equal obviously to 2x minus 16, and then this is equal to 2x minus 8, right? We can like take out this 2 from the absolute value, and then we see this x minus 8 piece, right? And then here in our given information, we see that x minus 8 must be less than delta. This is a piece that we're assuming. So we can say that it is less than 2 delta. Because we have this x minus 8 piece, we just kind of replace x minus 8 with delta and then change our sign to less than. Okay, so what are we trying to show again? We want to show that this implies that, well, I won't put it there. We want to show that our given pieces of information show that the distance between 2x plus 1 and 17 is less than epsilon. So you see here, we have this 2x plus 17, right? We already have this less than sign. But what is it less than? 2x plus 1 minus 17 in absolute value is less than 2 delta. We want it to be less than epsilon, right? So then we want to be able to get from 2 delta to epsilon. So what value should delta kind of possess in order for 2 times that value to equal epsilon? So 2 times what is equal to epsilon? Well, obviously it would be epsilon over 2.
So thus, we're using a delta value of epsilon over 2 to kind of complete this proof, to show that 2x plus 1 minus 17 an absolute value. We use this piece of information that this is less than epsilon. And we just showed the consequence, meaning that we have proved the limit. So this might take some getting used to, but this is kind of the format you would use to uh, prove a limit formally. You would kind of start at where you want to get, and then you would try to use your given pieces of information by making a form that is usable, like this here, by conducting some algebraic manipulations. You would substitute in your delta value, so we have less than 2 delta, and then you would bring in your epsilon. You would make delta to have a correct value such that in the end we show that 2x plus 1 minus 17 is less than epsilon.